Kia ora, Year 12. This question is from the test that we did on Monday. It's quite a tricky parametric differentiation question. I'm going to go through it quickly before we get into it. So we've got the parametric equations of a curve, and this is the curve here. I actually haven't had a look to see what that looks like. I'm sure it's something cool. If you want, you can put that into GeoGebra and have a play around. Right, but what's going on here is that I've got a parameter t, and it's affecting x, and it's affecting y. And that means that indirectly, x and y are moving together. The first part of the question is just to get dy by dx in terms of t. So we know that we're going to do that by finding dx by dt and dy by dt. That's going to be step one for that question. Then we have to find the equation of the tangent to the curve at a point with parameter t. And that means that the point is just back to this thing up here. Notice that my equation of the tangent looks weird, right? It's got x's and it's got y's, and then it's got t in there as well. So if you picture it, what we've got happening is, not for this example, suppose that I've got some kind of funky shape like this, right? So this is a point t. There's a particular value of t here. And what we're trying to do is find the equation of the tangent to that curve, right? And so as t changes, the point on that curve is going to change and the tangent line is going to change. And so the way we've got it here is that that's why we end up getting t in here as well as the x and the y. The last part is actually really easy. When we get that far, we're going to draw a little graph looking at where the tangent meets things using what we did in part 2. So as usual, if you get stuck on part 2, this is a show that question and this is a hence question. So if you know that you're working with this, then you can use this for this, and it's fine. This is the hardest 3 marks of the question. This is really easy, but a lot of you, I guess, probably freaked out at the second part and then just moved on. So remember, always look at the next part and see if you can do it without the part before. All right, let's get going on the first bit. So we've got dx by dt is equal to a times cos to the power of 4t. No, we haven't. That's what x is. Okay, try again. So x is equal to that. And for dx by dt, I have to use the chain rule. So we're going to have 4a cos to the power of 3t. Now I have to times by the derivative of the inside function, which is negative sine t. And then y is equal to, I'll clean that up in a second, but y is equal to a sine to the power of 4t. dy by dx is equal to 4a sine cubed of t times cosine of t. Now, we put those together, and I've made a mistake in there. That's dy by dt. Sorry, guys. Right, so dy by dx is always in parametric equal to dy by dt times dt by dx, using the chain rule again. And dy by dt, we've got, if we're timesing by dt by dx, that's the same as dividing by dx by dt. And we can write that as y dash over x dash. So what we're going to do now is we're just going to combine these and chuck them in. So dy by dx is equal to 4a sine cubed t cos of t over negative 4a cos cubed of t sine t. Cleaning that up leaves me with negative sine squared t over cos squared of t, which is negative tan squared of t. All right, now we're going to find the equation of the tangent line. Now there are 2 ways to do this, and some of you did y equals mx plus c. And that was nice. That actually, I think, worked out better than the way I used, which is to use y minus y1 was equal to m times x minus x1. This video is going to get a bit long if I do both ways, so I'm just going to do the way that I've done it in my printed word solutions. Right, what do I need to use this? Well, I need something for m, and m is going to be dy by dx, and my x1, y1 point looks a bit different, right, because it's just this. So I'm going to substitute this and this into that equation. Then I'm going to do some manipulation and try and get it over to this. X sine squared t plus y cos squared t is equal to a sine squared t cos squared t. Right, so this is our goal, so we want to keep one eye on that. Right, so pause the video and give it a go, see if you can finish it from here, but please watch right through till the end. So we get y minus a sine to the power of 4t is equal to negative tan squared t, so that's m, and then x minus a cos to the power of 4t. Right, we're going to clean that up carefully. We get y minus a sine to the 4t is equal to negative sine squared t over cos squared t x plus a. Now it's going to be cos to the power of 4t. Here I've got sine squared t over cos squared t. I'm actually not going to simplify this for now, right? I mean, you can simplify this as you want, if you want. But what I'm noticing is that I've got a common denominator here of cos squared t. I'm going to times the left-hand side through by that. So we're multiplying both sides by cos squared of t. That gives me cos squared of t y minus a sine to the 4t cos squared of t equals negative sine squared t x plus this stuff here, a cos to the 4t sine squared of t. Right, now just a little bit of rearranging. We'll get this x over to here by adding it, and we're going to add this over to here. That leaves me with x, what am I trying to write? X sine squared t plus y cos squared t is equal to a sine to the 4t cos squared t plus a cos to the 4t sine squared t. Now this is not quite in the form that we want. You can see that we want to end up with this, but we've got both of those bits on the left-hand side. So let's take out some common factors here. We've got a sine squared t cos squared t, and look at that. Here we've got a sine squared t, and here we've got an extra cos squared t. And we know that that equals 1. So we're done. Well, hopefully some of you are still watching, maybe not. So we've done nearly all of the hard work in this question now. Let's just scoot back up to the top of the screen and see what the last thing to do is. Okay, hence, here's your big clue. Show that if the tangent meets the x-axis at P and the y-axis at Q, then this has to be true. So let's think about what we've got with the tangent. Well, it meets the x-axis at P, put a point P down here, and it meets the y-axis at Q. Now, it doesn't have to be in those quadrants, but that will do. Right, what is our distance, OP plus OQ? Well, OP is just out to here, and OQ is up to here. All I need to do is figure out the y-intercept and the x-intercept for this equation. So when x equals 0, we have y, what do I have? Let's have a look. We've got our tangent equation, so we've got y cos squared t plus 0 is equal to a sine squared t cos squared t. So why, do we know that cos squared of t is not equal to 90 degrees? Let's go back and have a look. But I'm going to divide both sides through by cos squared of t, and I get y is equal to a sine squared of t. Now I'm just hesitating because I don't like dividing through by trig things. So let's go back to the very start. Oh, look, we're told that a is a positive constant. All right, well, we're going to assume that, I'm just going to hand wave, all right? So we're dividing through by cos squared of t. So y is equal to a sine squared of t. And when y is 0, we've got the other way around. So x sine squared of t is equal to a sine squared of t cos squared of t. So x is equal to a cos squared of t. So we've got those two. Right, let's draw that. I'm just going to draw some decent axes because this is, I hope no one's watching who's being disapproving of my lack of straight lines with a ruler. There we go. Right, let's biff in some nice axes, get rid of the ruler. So where's y? Where's my y-intercept? It's up here, and it's at a sine squared of t. So this is O, and this is Q. P is down here at a cos squared of t. So OP plus OQ is equal to a cos squared t plus a sine squared t, which is equal to a into cos squared t plus sine squared of t, which is simply equal to a. All right, thanks for watching till the end, if any of you did. That's one of the questions done. I'll try and get through a couple more of them tonight.